My name is Nitin, and I'm from team 1455 Terrabats. And I'll be going over the KISS design process and kind of just give an intro on how you can design your own robot using the KISS process. Okay, so let's get started. So I'll just go over three main points on the KISS design process. So what is the KISS design process? How do we use it? And I'll give two real world examples, depending on how much time we have. So here, let's get started. So uh, what exactly is the KISS design? What exactly is the KISS design process? So the KISS design process, so for some reason the picture isn't loading here. I don't know why the picture isn't loading, but KISS design process basically just means keep it super simple. A lot of people also say keep it stupid simple. There's a couple of different variations on the term and the way it's been coined, but the main ideology is just keeping your robot and all its subsystems extremely simple. Um, so why do we use the KISS design process? So the KISS design process is overall just a fail-safe way of designing your robot. The reason for that is because one, you have simpler subsystems. So why is it important to have simpler subsystems? The reason we often have some simpler subsystems is because there's less points of failure in simpler subsystems, right? And another thing is that the less points of failure you have in your subsystem, the easier it is to fix in case something goes wrong in a match, right? So the KISS design process is kind of like a backup plan for things that go wrong in a match because you don't want to have a overly complicated robot. And if something goes wrong in a match and then you have another match, probably, I don't know, 10 minutes later, you're not always going to have the time to, maybe fix your slides, right? If your stringing broke or if a wire got cut, right? You don't have time to redo all your wiring if you have a more complicated subsystem. And additionally, adding on to the less points of failure, if you have simpler subsystems, this doesn't always mean like having an arm that goes back and forth. It can also just mean just a simpler motion, like a degree of freedom, right? That allows you to have less points of failure. So if you get hit in a match or if something happens in a match, then there's less. Your robot is more robust, and there's less likely there's less likelihood for the robot to actually break if something happened in a match. So yeah, that's why it's really important to have less points of failure by using the KISS design process. And another really important point of the KISS design process is quicker turnover between CAD to assembly. So this is really important in our power play season. So in our power play season, we did and this is something that a lot of teams actually do around this is something that a lot of teams do around the like different regions. It's the league system, right? In league systems, you don't have a lot of time to really iterate on a new design. So it's important that you have one design that you just can just optimize as the season goes along, right? So by using the KISS design process, we can have a quicker turnover between CAD to assembly. But what does that exactly mean? So when you build a simpler subsystem, that means that there's less things that you need to kind of iron out in terms of the complexities, right? Which means that you can prototype it a lot quicker than something that was a lot more complicated, right? And then if you're able to prototype it quicker, that means that you can see what are the issues with your design and then, fix it. And then, go back to your CAD and assembly pipeline, right? So it's just really important that you're able to have that quicker turnover between CAD to assembly. And that also goes into my next point of having longer optimization time. So this doesn't like entirely just mean about you know hardware fixes, right? This is also really important for software fixes. Like I can't stress this enough. Your software team needs time for any part of your robot, right? Like you can't expect your software team to just see a robot like maybe 2 weeks before the competition and then have them be able to expect all the things that could go wrong, right? So it's important for your software team to have as much time as possible to work on their just work on the robot, right? So this goes along my last point because if your robot is fixed faster, right, or if it's built faster and finalized, then that gives your programming team more time to optimize and make your simpler design even better using programming, right? Yeah, so this is just why we would use the KISS design process. I'll go more into this as I talk about our examples. Um, this is really weird. So, uh, here, let me show you this. Here, one second. Let me stop sharing really quick. Okay. For some reason, I had a bunch of different pictures in here, but they don't seem to be loading. It's really weird. Um, yeah, that's okay though. Let's pull up a different picture. Okay, so here let's. Okay, so let's just look at this. So the way I usually explain KISS to my students, right, whenever I'm talking about the KISS design process and why we use it, I like to think of the KISS design process as a path, right? Because all of your design processes are essentially just a path from the start of your season to the end of your season, right? So imagine that you're on this path, right? This is the park, and you're on this path, and you're here at the start of your season, and you need to get to here, right? This is the end of your season. So ideally, you would just take any one of these paths to get to the final destination, right? You could, go all around the path, right? There's a bunch of different ways you can go about getting to your end destination. But the way I like to think of the KISS design process is by instead of going along these paths, you can just cut straight across the grass and get to here instead. You're taking the most simple route to your final destination instead of taking multiple different other routes that could also work. You're trying to find out what's the most streamlined route to your destination. But that doesn't exactly mean that we're taking a shortcut, right? KISS does not mean a shortcut. I want people to realize that just because we're cutting across through the grass, it doesn't mean that there aren't going. That it doesn't mean that it's an easier design process. In fact, I'd say KISS requires more thinking and more planning ahead, and I'll explain why. So, how do we efficiently use KISS? So, we efficiently use KISS by first you have to establish your goal. Second, you have to identify your constraints. Third, you need to draft out your first idea. And I can't reiterate this enough. You need to draft out your first idea because most likely your first idea will not be your last, right? You need to have multiple ideas after your first idea, right? Yes, maybe your second idea will work, maybe your third idea, maybe your fourth idea. Maybe you don't even get like the best idea by your 100th idea, right? But that's okay. Um, yeah, that's okay, right? But it's important that you should always be drafting out your first ideas. That way, you know what might be too complex, right? And that goes on to 3.5, which is reiterating on the complexities. So after you've drafted out your first, second, or third idea, look at that design. Is there something that you don't really need, right? And if you don't need that, maybe you can find a workaround, right? Like how do we make this design without having that complexity, right? So it's really important to always draft out your idea, and that allows you to have those complexities all ironed out. I'll go through these one by one. Here, so establish your goal. And I don't mean this on like an overall, oh, we need to score a lot. That's not what I mean by goal. I mean by exactly each subsystem, what needs to happen, right? And not only for just overall what needs to happen for the subsystem, right? Oh, I want a fast subsystem, but like exactly what is required by the game. So definitely go through the game manual, see, oh, my drivetrain, it needs to be pretty fast. That way we can go back and forth really quickly, right? Or my scoring system, it needs to have a lot of extension. That way we can place on some high pedestal, right? So just make sure you're establishing your goal. And maybe you can write it down. You can talk to your teammates about it, right? And just have that kind of back and forth communication so that everyone is in the loop about what you need to what needs to happen with your subsystem. That's extremely important, right? Because if you don't identify your goal, you don't know what you can't do. And that's the second step, identifying your constraints, right? So figure out what you can't have on your subsystem, right? So let's go back to the drivetrain example. We wanted our drivetrain to be fast, right? So one of our constraints would be we want our drivetrain to be really light, right? That would be a constraint. So a weight of the drivetrain would be a constraint that we need to identify, right? So if we're figuring out what we can't have on our robot, maybe our side plates, right? If you're having a side plate or a lot of metal plates on your robot, maybe that needs to be a pocket, which basically just means cutting out parts of the metal to make it lighter. And that would just allow you to have a lighter drivetrain, which just overall allows you to have a faster robot. So you see what I'm doing there? I established my goal and I identified my constraints, and that allows me to reach my goal, right? And if you do that overall on all the subsystems, then when you put it all together, that would allow you to have more cohesive robot, right? And I also highly suggest identifying goals between subsystems, right? Oh, if our I don't know, if our outtake, the part that like places our game element, needs more extension, then maybe the rest of our robot needs to be lighter in order to counteract that more weight that we're putting, right? So you see how here I'm planning out exactly what I need and how I need it, right? That allows me to not run into issues later on, right? This goes back to the park diagram, right? So here, let me actually go back to that. So if you're at the start of the park path, even though you're cutting across the grass, right? This is a shorter path. There's still so much unknown here that you need to plan out for. Maybe in the path there's a lot of dog poop. Right? You gotta watch out for the dog poop. So you have to really plan out. Maybe I should be looking down while I'm walking. That way I don't step in anything. Right? Or maybe the grass is wet, so I should try not to slip. Right? So even though it's a like technically the faster route, it doesn't mean there isn't a lot of planning involved. That's why you need to identify your constraints and establish a goal. And then, of course, draft out your idea. Draft out your idea. It will not be your last idea. Please don't ever start on your last idea, right? Just goes like writing in school. If you ever do a writing assignment, your teacher always says, "Don't draft out your, don't submit your first idea." And it's true. Your first idea, it looks perfect, but when you look back on it, there's probably some issues that you could have ironed out. And then, yeah, reiterating on the complexities. And there's a picture here, but for some reason it's not showing up. Um, yeah, you can see the picture down there. Yeah, so definitely reiterate on the complexities. And what that basically means is not exactly, I'm not saying don't make a fun looking robot, right? I'm more of saying, oh, make a robot that does what you need it to do, right? So say for example, your robot is, so I actually had, I don't know if you can see that here. Yeah, so that's pretty small, but that's the robot that I had in the picture. Um, but yeah, you have to see what could go wrong with your robot. That's what I mean by complexities, right? So say for example, you have a lot of weight on the back of your robot, and then you have a big arm that's looking back, right? You're thinking, oh, I've made a lot of space for my claw in the front by putting everything in the back, right? But then we can see that, oh, when the arm flips back, what if the entire robot flips over? And you're probably thinking, oh, that's never going to happen. Why would we go back that fast? Most likely it will happen, right? So that's what you need to plan out. You have to plan out what could happen and then reiterate on those complexities. Let's see if this next picture will want to work. Okay, that's really awkward. Okay. Um, okay, let's zoom back into here. Yeah, so this is also pretty small, so you probably won't be able to see it. But basically, what's happening here is we have a robot for uh, the power play game from 2 years ago. Wait, here, how much time do I have? I'll just pull up the actual picture instead of having you guys wait. Um, Give me half a second. Yes, but it's really important to just like work on what is complex about your robot, right? Because if you aren't planning out these complexities, then you're going to run into issues later on in the season, right? Here, okay, one picture. Uh, okay. Okay, so this is a robot from PowerPlay. Um, as you can see here, this looks pretty complicated, right? It's actually from 12791, Iterative Intentions. And here's a couple of things that they could have done differently if they used the KISS design process. Also, full disclaimer, I'm pretty sure they knew 100% that this was a complicated robot, but they kind of started with it, and that's pretty cool. Um, but yeah, for example, in Power Play, the name of the game was basically to grab these cones off the ground and place it on these different poles, right? You see how there's these yellow poles? And you could have done it in a multiple different ways, but a lot of teams had a static like elevator system that just went up and down to place the cones on the different poles. But you can see here how Iterative Intentions and how he's just going to look at their robot. You can see how they just kind of spin around, right? Instead of just having a static extension system. And by having that added complexity, that's just another thing that could go wrong. Maybe it worked all the time, but if it's not necessary, why do you really need it, right? Like the turret, it's not entirely helpful, so you don't actually need it, right? So you got to really think about that. Like, am I by adding this part of my robot, is it helping my scoring potential? And if it's not, then you need to reevaluate whether or not that complexity is necessary in your design. There's some other stuff in this robot that's pretty complex, but I don't want to go over it all right now. But I highly suggest looking to this robot and just seeing, oh, what's something that they could do differently, and then apply that to your own robots. Um, yeah, I do think my 10 minutes are up. So if you guys have any questions, I did kind of go a little bit quickly. So if there's something you didn't understand, feel free to ask any questions right now. And I think there was a question.
Yeah, I think I saw a question in the chat.
There was a question. Let me. Okay, so someone asked, let's see, is there a point at which you shouldn't go any simpler? For example, a tank drive is simpler than Mechnum drive, yet a Mechnum driver is significantly better than a tank at maneuverability. Or direct drive is simpler than a chain sprocket, but worse for the motor. Okay, yeah, this is a really good question. And it's something that I kind of touched upon when I was talking about iterative intentions, right? So when you're identifying your goal, this is something you need to talk about, right? Figure out what needs to happen for the subsystem. So let's talk about Magnum drivetrain versus tank drivetrain, right? So especially last year, something that was really important for our game center stage was to be able to place pixels perfectly on the backdrop, right? And that meant that we needed a little bit of maneuverability at the backdrop. So then you need to establish a goal. My goal is maneuverability, right? And then when we're talking about our drivetrain, you have to be like, oh, um, would a tank drive have that same maneuverability as a Magnum drive, right? Then when you're thinking about those goals and you're identifying your constraints, you realize that oh, the scoring potential provided by Magnum drivetrains just allows us to have a better robot. So hence, we should just go with a Magnum drivetrain. You kind of see what I did there, right? Like a tank drive is simpler, but when we're establishing our goal, the Magnum drivetrain is more important, right? Keeping it super simple doesn't mean that, oh, we should just do a direct drive. It means that we should have more than we need, right? So it doesn't mean just like, like you're in a room, right? You're in a simple room. right? It doesn't mean that, oh, that room's perfect, right? It has everything I need. But you also want to like optimize like how much stuff you actually want in there, right? And then like also talk about direct drive versus chain and sprocket, right? Direct drive could make your robot wider, right? Because when you when you put the motors directly connected to the wheels, that means your overall robot is going to be a little bit wider than it needs to be. And then if one of your constraints, right? Remember, we're identifying our constraints. If one of our constraints was to have a slim robot, then when we're using the direct drive motor, then it won't be as slim as we want it. And then a chain and sprocket or belt drive would have had that same slimness, allowing us to have a higher scoring potential. You see what I'm kind of saying? Like it's not about having a super simple robot. It's also about having that same level of scoring potential. That's a really important part. Scoring potential. Um, yeah. Is there any other questions? I think
Yeah,
155 dot time. But yeah, if there's any other questions, feel free to ask. And yeah.
I think in the interest of time, we're gonna move on here. So make sure everybody gives a round of applause for Terrabat.